Okay, we're going to start this off by talking about alcohol nomenclature and reactions. Before we get to nomenclature, let's talk about identifying or classifying alcohols. They're going to be dependent upon what type of carbon they are attached to. So if you have a primary carbon, you have a primary alcohol. Secondary carbon, a secondary alcohol, and a tertiary alcohol would be on a tertiary carbon. So a primary, looking at an OH on a primary carbon, secondary an OH on a secondary, and a tertiary on a tertiary carbon. Nomenclature. Nomenclature for alcohols is very similar to what we saw with alkanes. The OH is the new functional group, meaning it's going to take the higher priority. We're now going to change our ending from our alkanes, meaning our E at the end, to an ol. So here we would have a methane, CH4 would be methane. We're going to replace that with a methanol. So our E becomes OL. We would have ethane here, so ethanol. Here, just like we would with any other functional group, we would add a number to where it's located. Again, you want to keep your first number as low as possible. So in this case, we have a 5-carbon chain with an OH on the third carbon, either coming from the left or the right. So the 3 signifies where the OH is, 3-pentanol. When we have competition between another functional group, alcohols are going to break the tiebreaker with halogens. So in this case, we could have R1 be attached to the alcohol or R1 be attached to the bromine. Since the chemistry with alcohols is more complex, they're going to be a higher priority. So R1 is going to be attached to our OH group, not our bromine. So this would be 3-bromo-1-propanol because our tiebreaker would have the OH having the number 1 priority. 4-chloro-2-butanol. So again, if you have the name, you can start by drawing your structure out. You know we're going to have 4 carbons. You're going to have your OH on the 2nd position and your chlorine on the 4th position. All our other nomenclature rules still follow here, where if you have 2 groups on the same position, you want a comma separating the number twice. Here again, notice that our OH is on carbon 2 and our 2 methyl groups are on carbon 4. I'd encourage you to pause the video and try these 3. Okay. Keeping in mind that with rings, we know the OH has to be on position 1, so we don't need a 1 signifying where the OH group is, but our numbering system is still going to count from that position. For the second one, in this case, going from left to right, the OH is always on position 4 since we want the lowest order of numbers. We're going to have our 2 methyl groups, so it's okay that the methyl group has a lower number because if we started from the other direction, it would be a higher number in the front. Here, same issue. OH is either number 3 from either left to right. We want the lowest number for the other substituent, so 2-chloro-3-pentanol. Pause the video again to try these 3. Okay, in the top one now, we have a clear way to identify where the OH group is, meaning that it's definitely going to have a lower number starting from either the left or the right. And here, starting from the right, we know that that position is going to be 2. We look at our other positions. Remember, at position 4, we have an ethyl group. At position 6, we have a bromo. Alphabetically, the B comes before the E. That's why our bromo would need to come first. Same thing here. We're going to go in order of the lowest second number since our OH needs to be position 1. Going counterclockwise would get a substituent at position 2. Going clockwise would get a substituent at position 3. So we have 2-ethyl-5-methyl-cyclohexanol. And here we have the same order no matter which way you go, counterclockwise or clockwise. It would be 3 and 4. And again, since it's a ring, we don't need a designation of 1 on the alcohol. Let's talk a little bit about the chemistry. When we last left off, we started talking about SN1, SN2 reactions. And here we have a primary alcohol on a primary carbon. And we know that the only type of reaction that could happen at a primary position would be an SN2. Unfortunately here, if we have a Br minus trying to complete an SN2 reaction, it's going to kick off a strongly basic leaving group, which would be OH minus. So if this reaction actually could happen, the reverse would also just kick out that bromine, right? Remember, for leaving groups, we want weakly basic leaving groups, and OH minus we identify as a strong base. So as you're going through reactions or predicting products, make sure you are not ever having a strongly basic leaving group. What we can do is, in order to make an SN2 reaction happen here, we need to make the OH into a good leaving group, which we can do with acid. So we can protonate the OH, making a great leaving group, water, and here with heat we can force that OH group to be comfortable being kicked out. Our bromine can come in at a primary position, and we now have a substitution reaction. So in order to do this, you're going to need to see acid, and usually you'll see it accompanied with heat, depending on what type of alcohol you have. So take a second, pause the video, and try to predict products here. Just like with substitution reactions earlier, we see that the same product's going to occur. The mechanisms is what's going to be different, whether you're at a primary, secondary, or tertiary. Notice for your reagents here, for primary and secondary, you do use heat, while for tertiary you don't, and you should be able to think about why that is. For products, it's going to be very straightforward substitution reactions where our OH would be replaced by our nucleophile of iodine, replaced by our nucleophile of bromine, and again replaced by our nucleophile of bromine. So keep in mind, primary and secondary alcohols need heat, tertiary alcohols do not. Let's talk about the mechanisms for these. The first step is going to be that using the lone pairs of the oxygen to go out and grab that hydrogen, kick off the bromine. This is going to allow for the carbocation to be formed. Remember, we have a good leaving group here, meaning the oxygen can take the electrons from that bond, get them back, and at this point we've now created a carbocation that can then add the nucleophile, bromine coming in. Remember your arrows always starting from lone pairs or negative charge, and here we now have our substitution product. If it's a primary alcohol, know that we can't create a carbocation, so we're going to actually have an SN2 reaction. We're still going to have the same first step where we're going to protonate the oxygen. In this case, we can draw these two arrows in the same picture because it's an SN2 reaction. Remember, stereochemistry would change if we had a stereocenter, but here we have backside attack, the bromine coming into the electrophilic carbon. Remember, despite the oxygen having that positive charge, oxygen is still more electronegative than carbon, so that carbon that is attached to the now positively charged oxygen is still electrophilic. So if you're thinking about how to draw mechanisms for a reaction, you're looking at an SN1 reaction unless it's going to make a primary carbocation. So for secondary and tertiary, you're looking at drawing an SN1 mechanism. For primary, it would be SN2. Keep that in mind. As always, we would never make a primary carbocation, so it's an easier way if you're drawing it out and you make that, you know you made a mistake. The other reaction that can take place is if there is not a good nucleophile around, and remember we've talked about H2SO4 being a non-nucleophilic acid, we can protonate the OH and actually have that leave, creating an elimination product. Notice here we have heat, and let's talk about this mechanism. Secondary and tertiary alcohols are going to go E1 reactions, so think about the arrows the same as for our substitution reaction we just talked about. Our OH coming in, grabbing the hydrogen, again having your arrow go towards the sulfonate group. At this point, since it's a secondary, we can have our water leaving group leaves, making a secondary carbocation. We also have water around because the reaction's happening under acidic conditions. So water can come and take that hydrogen. You've now made H3O plus and your elimination product. Remember, For your base, for the elimination reactions, it's going to take a hydrogen from the carbon next door to your carbocation. If you look at both of these, we now have options as to what carbon we will take the hydrogen from. Remember our rules, we're looking at making the more substituted product, so we are going to have a regioselective reaction here, where our H2SO4 is going to allow us to have a major product of the more substituted double bond with 84% and our less substituted double bond at 16%. Remember our rule, when you're deciding which carbon to take the hydrogen from, you're looking for the carbon that has the least number of hydrogens already. Here in this case we have another, really 3 carbons, but 2 of them are the same on the ring. So here we're going to have a higher percentage of the more substituted product with the double bond going in the ring versus going out. So the major product is always going to be the more stable alkene.